Hey guys, I have a demonstration here and we're going to be looking at electromagnetism. And for the first part, I'm going to have a couple demonstrations, I'm going to do some lecture, and then you're also going to be doing a lab on this as well. Some of the same principles that you'll be seeing in the lecture we'll be doing is actually part of the lab. So what I first want to show you is that I have a setup here, and the setup includes a battery, some wiring, and a stand, and also there's a compass here. The compass is currently facing to the north because that's the direction that north is inside of my room. And currently the magnet, which is the compass, is responding to the Earth's magnetic field. However, what I'm going to do is I'm going to complete the circuit, and I'm going to tap this alligator clip over the other electrode of the battery, and you'll see what happens. What's happening is that the compass is now responding to a new magnetic field. Where is that magnetic field coming from? It's coming from the actual wiring. So we're going to take a look at this concept of electromagnetism. So this is going to be section 24.1, number 2. And this is electromagnetism. There's two things about electromagnetism. The first concept in electromagnetism is that magnetic fields can create electricity, and electricity can create magnetic fields. So let's look at the first one, and that is electricity creates magnetic fields. That's what we just saw in that demonstration. We saw that the magnet, which is the compass, responded to the magnetic field that was created by electricity. What we'll also see is that not only do electricity create magnetic fields, but magnetic fields can create electricity. Magnetic fields create electricity. And this is seen in hydrothermal dams, where the water pours through the chutes of the dam, and there is a giant propeller, like a water wheel. And attached to this propeller or this turbine are magnets. And the magnets, when they spin, they actually push the electrons through the wiring to create electricity. So let's take a look at a couple of things, and that's going to be what are called right-hand rules. We're going to take a look at the first right-hand rule. The first right-hand rule. So a couple of things. We're going to be using your right hand and not your left hand. So if you look at, I have my fingers pointing in this direction. My thumb in this orientation is going to be pointing in the up direction. So here is a setup that we'll be seeing in the lab. Imagine that you have a note card. So here is the note card. This note card is going to be seated atop of a styrofoam cup. And there is going to be a wire that's going to go through the bottom of the cup, and it's going to come through a hole in the card, and then this is going to be connected to a power source. So just like we saw with the compass, when we complete the circuit, we're going to have current running through the wire, and that is going to create a magnetic field. Well, in which direction is the magnetic field going to be created? Well, if the current is running in this direction, and we're going to be using our symbols from last semester, current is going to be symbolized with the letter I. So let's go ahead and do this. In the first right-hand rule, if my thumb is pointing in the direction of the current, what's going to happen is the magnetic field is going to be created perpendicular around the wire in all directions. So we've established that the current is going to be running up the wire like this, okay? And what's going to happen is, again, the current is going to be, the magnetic field is going to be perpendicular to the wire in all of the directions, meaning it's going to be perpendicular here and perpendicular here. If you put a compass on this paper, which we'll see in the lab, it will be pointing to the north here, but on the other side, it'll be pointing this direction, as if this is north. So it's obviously not responding to the Earth's magnetic field. It's responding to the magnetic field that's being created by the electrical current. So if you follow this all the way around, of course, north would be pointing this direction, to the left, over here. And if you had a compass right here, it would be pointing to the right. And it looks like that the magnetic field goes around in a circle. And it's actually created, the magnetic field is created perpendicular to the wire around this wire. And again, the current is running in the up direction, and if you have your thumb pointing up, your fingers are the direction in which the magnetic field are going to be created. So it's going to be curling around the wire like this. I hope that's able to be seen. So the wire is with the current, and it creates the magnetic field. And the magnetic field travels in a circle around the wire perpendicular to the current. So we have the magnetic field is going to be around the wire It's going to be also perpendicular to the current. So imagine that we have a battery like this. Let's just say it's a C battery or a D battery, okay? And even though this is the positive and this is the negative, in chemistry we talked about the electrons coming out of the negative terminal, which is the anode. But again, because of Benjamin Franklin, things have been switched around in electrical terminology. This positive actually is the anode, and that's where the electrons are going to be coming out from. So they're coming out in this direction and going around in this direction. So here's the current. Okay. So in which direction will the magnetic field be created? Well, it's going to be perpendicular in all directions to the wire. So if you now follow this current in this orientation here, your thumb is going to be pointing like this, and that means your fingers are going to curl around the wire. They're going to be going around like this. They're going to be going over the wire here, yet under the wire here. They're going to be going over the wire here, yet under the wire here. Okay? Going to be going over the wire here and under here. Keep going around, over the wire here, and then under here. So if I have a compass and it's sitting above the wire, here's a compass, and here's a compass that's down below the wire. In which direction is the north going to be pointing? Well, on the top, it's pointing this direction, this direction, this direction. North would be pointing like this. But if you take that compass and put it on the underside, you have the magnetic field going on the underside in that orientation. And so it would appear that north would be in that direction. So this is the compass when it's above, and this is the compass when it's below. So with the first right-hand rule, again, you take your thumb is going to be the direction in which the current is traveling, and then the magnetic field will go around the wire as your fingers curl around the wire in that direction. So what we're going to do now is we're going to take a look at the second right-hand rule. It's going to go on the back side of this. I'm just going to new page. So here's the second right-hand rule. And the second right-hand rule is looking at electromagnets. So I have a demonstration here to share with you. What I have here is going to be my source of my current and my power. And on the inside of this is a giant coil of wires. So one wire would make a magnetic field. 2 wires would be doubling that magnetic field. 3, 4, 5, 6, 7, etc. You are multiplying the strength of that magnetic field based upon the number of coils of wire that you have. These coils are called solenoids, which we'll get to in just a minute. So right now, there's no current running through, so this is just iron, and this is just iron as well, and there's no real attraction between these two. If I attach this here, it just kind of falls off. However, if I put this battery in here, and I attach this on the bottom like that, it becomes a little bit stronger. So I now have this, it's not falling off. If I apply some force, I can then take it off. There, it's kind of a little bit stronger there, more strong attachment. Actually, I'm pulling pretty strong, and okay, I can pull it apart with a lot of strength. That's because of the amplification of that wire on the inside here, and enough strength will get that undone. So here's the second right-hand rule. So we're going to be using the first rule to determine the direction of the pole of the electromagnet. Okay, so we're going to use the first rule to determine the direction of the North Pole in an electromagnet. We'll also do this in our lab. So also, again, this increasing the magnetic field can occur when you have multiple wires. And when you have multiple coils, that's called a solenoid. Multiple coils, again, is called a solenoid. So imagine that we have a nail, and this nail is like this, and I'm going to take a wire and I'm going to wrap it over, and then it's going to come under. Okay, over, and it comes under, over. Okay, this is how it's drawn. Okay, over, and then it comes on the underside. So it's going over here, it's coming on the underside when you are at the other end. So in which direction is the north going to be? Well, if the current is traveling in this direction, so here's the current traveling in this direction, we're going to be, again, using that first right-hand rule. The fingers are going to coil, though, in the direction of the current. So in this case, though, instead of using my thumb, I'm going to use my fingers. Fingers are going to coil in the direction of the current. So in this case, notice how it's going over the nail first. It's going over, then under, over, then under. So it's going over, okay? Since it's going over and it's curling around this way, notice which direction that my thumb is pointing. My thumb is now pointing off to the left. That actually becomes the north. And so therefore, this is going to be a south. And again, when this is connected to the battery and this is running through, what happens is it creates a magnetic field, and that actually magnifies the nail, and the nail becomes a temporary magnet. The nail becomes a temporary magnet. Okay, let's see what happens if we switch this. Imagine that we come with the current in the same orientation, but we come on the underside first, and then come over, then come on the underside, okay, then go over, go on the underside, okay, kind of keep following that pattern, and then it comes over the nail at the end over here. So the current is running in the same direction, however, we're going on the underside first. Well, let's follow that, okay? If you follow with the current and your fingers are going to be the current and they're going to curl over the nail like this, notice how my thumb's going to be pointing off to the right and the thumb points to the north. So you're using your fingers to coil in the direction of the current, and the thumb points to the north. If you go over this way, it points to the north here. If you're going on the underside, then over, north is going to be this way. And there's two things that will affect the strength of this magnetic field. And the first one is the amount of wire. The more wire that you have, the stronger your magnetic field will be, and the stronger your magnet will be as well. One other thing that will increase the intensity of this magnetic field is the current. The more current that you have, the stronger that your magnet will be. That's it for 24.1, number 2.